a minute. Okay, one atomic layer per minute on a dense or two closely spaced structures. We result. Okay, this one. Uh, like when
Yeah.
you're depositing something on something else. Say you have some
Okay.
structure in silicon, some lines and closely spaced lines, or some structure in silicon, and on top, if you're depositing
Hmm.
SiO2. Now either you can do a conformal
Hmm.
SiO2 deposition, or it might not be so conformal. So
Yeah.
there might be like if there are two lines coming close to each other, they're saying if it is conformal deposition, that will create some space between the SiO2 that is deposited on top of it. Okay.
Okay.
Uh, can you see my screen here, the other device?
No. No.
Okay, just a minute. Okay, 1 second. I'll again join the meeting on the web.
Okay.
Hello. Yeah, sorry for the delay.
That is visible. Yeah.
Okay. So say this is my structure, okay? Is it writing? Today my
Mm-hmm.
writing pad is not there. So this is the structure that I have. So, so I have very closely spaced structure. It might sometimes happen that when I am depositing on top of this, right, it will deposit here, but some place in between might remain like a void. So it will deposit on this edge, it will deposit on this edge. Some place in between might remain void. Now your question is, will this happen in case of conformal deposition or in the other case? That you have to find.
Okay. So
We just discussed in
the
class.
gap which created. Okay. So
Yeah,
the gap which is created, that is called a void, right?
true. That is the void.
Okay. And one last approach I just want to know on question number 8. It says, if you read it, then I will be able to uh, clarify the approach.
If a solar cell manufacturing company makes a module in 2 minutes and each module consists of 60 cells, wafers, keeping throughput in mind, which of the following processes can be accommodated in the production line? Spin coating,
So
dopant.
there are times given for each processing, and by the calculation of it, the 60 wafers, if we calculate for the time for manufacturing or processing those 60 wafers, if it comes like below 2 minutes or 120 seconds, that option should be correct. This should be the approach of what.
Yeah, like how, like maximum number of wafers in minimum time should be the approach, right?
Okay, because the time is fixed here, 2 minutes. It takes 2 minutes for 60 wafers. It
True.
should take. So if the process or each any one of the process takes less than that time, then I can say that that process is accommodated in the production line. That should be accommodated, correct?
Just a minute. 2 minutes and each module consists of
Yeah.
60 cells. Yeah, all the 60 cells should be processed under 2 minutes. I think that is the idea.
Okay. So because there are many wafer, there are many times you can see that for unit processes, those unit processes takes like the more than 2 minutes. So those processes is discarded, right? Because it cannot hold that criteria of 2 minutes. So we can't take that in the production line. That should be the approach, I think. Out of four, only one uh, unit process is there which takes below 2 minutes
Yeah.
if you calculate closely.
Okay,
So
that
that
should be
should
the
be the
answer.
answer.
Yeah, yeah. I think so.
Okay.
Yes.
Okay, fine. That was it. Only just, ma'am, please find out about question number 7 and just mail me. Yeah.
Sure, sure. The second and the third point, right? Yeah, I'll
Exactly.
try to search about
Meaning
it.
of it.
Yeah.
Okay.
Okay. You try to like find in the lectures itself, it might be there. Like most of the questions that Prof has given till now, they were somewhere in the lectures. So I don't know. I have not seen all of the topics.
Exactly.
Yeah.
Exactly. The first part is in the lecture, but the second part is not in the lecture.
Arish.
Like
Okay.
it's nowhere. It's nowhere there. Like how FTO deposition is done. It's nowhere there. Like in any of the lecture from start till the end.
Okay.
Not in the latest ones also for this
Okay.
like
Okay.
week 12 also. So
Okay. I'll let you know.
sure,
Uh,
ma'am.
yeah. Thank you. Mir also had some question. Do you want to discuss it now or after the class? Kifayat. Hello. Okay. Okay. Sure. Okay. So we'll start with the class. Uh, so today I have a very short class, like only 10 questions, multiple choice. Since I'm at my hometown, it will be difficult anyways. Let's start as soon as possible. Okay. So yeah. So the first problem is high vacuum is maintained during electron beam evaporation. Select all the statements that correctly explain the reason for this. Okay. So, yeah, so in your exams, you will usually get questions like this. So, first you have to think like from which portions it is coming from. So, they're telling about electron beam evaporation. So, what technique is this? It's a deposition technique, obviously. So, is it physical vapor deposition or chemical vapor deposition? So, anyone wants to answer? So, it's evaporation, right? Yeah, PVD. Thanks, Sarla. So, it's a physical process. It's like the name suggests, we will have some, so we'll usually have some material that we want to deposit on a substrate. So if this is my substrate, sorry, if this is my substrate and I want to deposit some film on that, and uh, yeah, so I'll basically have some material that I want to evaporate. So it will evaporate and deposit on the film. So this, can you see the screen? Like I don't see any updates on my screen, so I'm confused. No, right? Okay, in that case, we will. Yeah, it is getting stuck. It's okay, so I won't be writing on the screen anymore. I'll just share the screen from my laptop itself. Sorry for the interruptions today. Yeah, so can you tell me which of these would be the correct option? So we know that electron beam evaporation is a E-beam evaporation is a physical vapor deposition process. So all physical vapor deposition processes, usually what happens is we have, like in evaporation, we will have some material, we will evaporate it and deposit on the substrate. And so like if the material has to transport from one place, that is our like it's getting heated at one place and it's transporting in the vertical direction towards the substrate, then what will happen if the pressure is high? If the pressure is high, that will mean that there are more number of particles in the chamber. So if all those particles are there in the way of the vapors, then that will mean that um, one, that they might also get deposited on the substrate, and two, they might obstruct the. You're saying something? Yeah, Mir. 3. Deposition rate is reduced by scattering at high pressures. True, thanks. So that is indeed true. So there will be scattering uh, because there will be particles in the chamber. So that is one of the answers. But there, like I'll give you a hint. There are more than one correct options here. So what might also happen that, so say I'm not at very high vacuums, so there are some particles present in the chamber, so they might also react with the material I'm heating. So I'm going at very high temperatures, right? Because I have to so even if my substrate might not be at high temperature, but the the alloy or the metal that I'm trying to deposit, that will go at very high temperatures. So that might react with say whatever is present in the environment. If there's oxygen or some like if the vacuum is not high enough, it might cause unwanted reactions to happen. So even one is the correct option. A also, right? You are correct. Any deposition techniques require such a high vacuum? That's definitely not the case. In fact, in CVD, we don't really need high vacuums. High vacuum is desirable in case of very good deposition, but we can do even at atmospheric pressures and all. APCVD is there, right? Some precious metals will start evaporating only at such high vacuums. That's not the case. Which one of the following statements are true about thermal evaporation? It is difficult to deposit refractory materials like Al2O3 or tungsten. So, what are refractory materials? So, first of all, about thermal evaporation. So, it's again the same technique of thermal evaporation. In this case, they were saying electron beam evaporation. So, the only difference here is in electron beam evaporation, we don't really evaporate the entire, say, entire source material. So, basically, if I want to heat up metal or some material to evaporate it, one thing I can do is I can do some resistive kind of heating. Another thing that people usually do is electron beam heating. So they will direct an electron beam and direct it to the material, and only some portion of the material will melt and if start evaporating, and rest of it will remain cold or at room temperature. So so this technique is widely used when we don't want cases like say I want to heat tungsten, but then the crucible on which I've kept the tungsten might have some sodium impurities or some other kind of impurities, and because the entire thing gets heated up in resistive heating techniques like using thermal evaporation, then we'll have more impurities, right? So we don't want those scenarios. Then we'll use electron beam. So so the other situation is thermal evaporation. Thermal evaporation basically means just resistively heating the entire material at one go. So that is the difference. It is difficult to deposit refractory materials like Al2O3 or tungsten. Right. So what is refractory materials? Refractory materials are basically materials that can withstand very high temperatures. So if something is withstanding very high temperature, what does that mean? Its composition does not change much with temperature. It won't melt, it won't start evaporating. So this is in fact true. So if I have some refractory material like Al2O3 or tungsten, it becomes very difficult to deposit using thermal evaporation. Like even if you don't know much about the material, just by knowing the fact that it is a refractory material, you can say that uh, it won't be possible for thermal evaporation. Alloys can be easily deposited. Is that true? Can you really deposit alloys using evaporation? So it's possible to actually deposit alloys using physical vapor deposition, like in general, but for the process of exact process of evaporation, it might not be possible. It is not possible to deposit the exact composition of the alloy. So that is because uh, different materials in an alloy might have uh, different boiling points or vapor pressures like at a particular temperature material has a particular vapor pressure, right? Similarly, another material might have some other vapor pressure for the same temperature and pressure conditions. So the rate of deposition of first material compared to the second material will be different, and because of that, yeah, so that is false. Melting point will differ. The arrival angles are usually very diverse, so deposition is often conformal. Uh, so, in what cases will arrival angles be different? So, when our material is evaporating, if it encounters many particles on its path, then it will get scattered, and then it will have very diverse arrival angles. But in evaporation, we are starting with the fact that we want very high vacuum. When in case of very high vacuum, usually there will be no scattering or very less scattering, and because of that, the arrival angles will not be that diverse. It will usually just go straight up, and incident our substrate at 90 degrees or whatever is the wafer orientation we have kept. And so the deposition won't be conformal. So this is also false. The deposition can occur with substrate room temperature. Is that true? True. Yeah. So yeah, it's true. So we can keep the substrate at room temperature. We just need to heat the material that we want to deposit. Right. So okay. The primary and secondary, if present flat on the silicon wafer, indicates. So the picture is quite explanatory. It will actually give the answer away. But yeah, so what is a flat on a silicon wafer? So usually when we buy silicon wafers, they will have these flats. So there will be one small flat and a longer flat. So the longer one is called primary flat and the shorter one is called secondary flat. And based on the orientation of these flats, we are able to guess whether we are having a 100 type, 111 type, N type, or P type. So basically, they help us in knowing if the crystal orientation and the dopant type. Unfortunately, there is no way of knowing doping concentration or yeah, or the wafer production technique. Yes. So yeah, so if my two flats are opposite to each other, I'll simply say that it is 100 N type. So I don't even need to know yeah, the crystal orientation. So there are different combinations of these angles that they have made and they have standardized it, so we can easily tell the orientation as well as the dopant. Okay, 30-minute anneal in N2 at the end of oxidation cycle is recommended for which of the following? Uh, okay, so first of all, where is this coming from? Oxidation cycle. Whenever we see oxidation, like it probably means native oxide deposition. So in native oxide, basically we have silicon and then we oxidize the top layer of silicon to form SiO2. So it's a way of getting SiO2 on top of silicon. So after the oxidation, a 30-minute anneal in N2 is recommended. So what does this N2 will do? Will it reduce fixed oxide charges? Will it reduce interface trap density? Will it reduce oxide trap charges or ionic charges in SiO2, in bulk of SiO2? So these four were the primary defects that we know of in SiO2 that is formed by native oxide growth. So to answer this, first of all, let's try to remember what were these four type of defects. So fixed oxide charges are uh, okay. So when I have SiO2 deposited on, okay, yeah, Komal has joined. Huh. So when I have SiO2 deposit native oxide SiO2 grown on silicon, the SiO2 that is uh, close to the silicon interface, it might not be exactly SiO2. So it might be SiOX, like SiO 1.5 or SiO. So it might happen that silicon has some dangling bonds that are the valencies of which are not satisfied. Some of the silicon atom valencies are not satisfied, and that is basically the interface trap density. And because this SiO2 is not complete, so there might be some charge that is formed at near the interface. That is the fixed oxide charge. And yeah, so these two are basically the interface phenomena, and the other two are the bulk phenomena. So there might be some charges that are trapped in the bulk oxide. So when I have an oxide that is deposited, it might randomly uh, there might be some places where the bonds are broken, some places uh, there is an extra electron, some places the electron has escaped into the voids or something. So because of that there are some trap charge in SiO2 and these are random processes. So this has nothing to do with our deposition step or anything. It might happen in some like PECVD deposited SiO2 also. And there might be also mobile ionic charges. So these come along when we are doing any kind of deposition because of the furnace that we are using, or all kinds of contaminations present on the wafer holder, or so even though we want things to be clean, there might be some contamination like sodium ions or potassium ions, or any other kind of metal contamination that might come in, and that might give this mobile ionic charges in the bulk of Si2. So these two are random processes that happen in the bulk, and these two are happening at the interface because of the unsatisfied valencies near the interface. So now the question is, which of these will the annealing step help in reducing? So do you want to take a guess? Not able to draw a deal triangle here, but if you remember, the deal triangle was, uh, it basically showed, on the y-axis it showed the defect density, and on the x-axis the temperature. So the defect density will usually decrease with increase in temperature for dry oxidation. So here we are doing native oxide growth, right? So we will be doing dry oxidation, and if we do this dry oxidation at higher temperatures, then the defects will be low. In addition, now I'm at high temperature, and so dry oxidation I'll do in O2 ambient. But now if I remove the O2 and give N2 ambient and even reduce the temperature, then even after reducing the temperature, the defect density will remain same. Okay. And okay, so what if I am not able to go at such high temperatures? In those cases, what I can do is I can actually oxidize at a lower temperature, and then when I give an N2 ambient, so nitrogen anneal, what it will do is the reaction is such that, uh, or not reaction, the anneal is such that the so annealing in N2 ambient will actually bring it to a defect density point that is equivalent to, I'll do one thing, I'll try to search for a Diels triangle. Okay. It seems unlikely I'll find a good image. So let's just go back. So okay, I'll just tell the moral of the story. From the Diels triangle, we can say that when we anneal in N2 ambient, we'll get to a lower defect density, which is as good as the defect density that I would have got if I had done oxidation at a higher temperature. So we might not be able to reach some 1300 degrees Celsius temperature for dry oxidation. So what we might do is we do a dry oxidation at say 900, 800 degrees Celsius, and then anneal it in N2 ambient. So that will help in reducing the fixed oxide charges. So that will reduce the defect density of fixed oxide charges. So this is actually true. So one is the correct option. Two is an ambiguous option. So we actually it's very difficult to say. So when we do a H2 plus N2 anneal, so forming gas anneal, uh, then it will help in reducing the interface trap density, because in that case the silicon dangling bonds will be satisfied by the hydrogen in the forming gas. However, uh, it's also true that by just doing the N2 anneal, it will help the oxide to settle, so all the SiO to fill their valencies, and it will to some extent help in reducing the interface trap density also. So actually the correct answers are both 1 and 2. 2 is in my opinion a bit ambiguous um, because usually for reducing the interface trap density we will do a formic gas anneal. However, both 1 and 2 are correct in this case. Is that okay? So usually annealing will help in settling things down. So when we are doing one process after the other, it might happen that not all the bonds are made properly. Since annealing in a way helps in like completing the reaction. It gives the products to settle down to some, how to say. So it will only make changes in places where the reaction is going on. It will usually affect only the interfaces, or so it won't make any changes in the bulk. So what like say about mobile ions, right? It might just happen that by annealing in nitrogen ambient, these ions might diffuse even further, or they might diffuse out of the material, but they won't there won't be any considerable change in the bulk because of this annealing processes. Annealing processes will only um, cause a change at the reaction sites, so in this case the interfaces. So that's why I think the first and second option are correct. Okay, so yeah, silicon 100 is more popular in CMOS industry compared to silicon 111. Why is that the case? So the options they have given is it's easier to grow using CZN method. So is it true that we can easily grow silicon 100 but it's more difficult to grow 111?
No, ma'am.
No, right? So yeah.
That,
Why do you say so?
um, actually, na there, ma'am, there are three planes: 100, 111, and 110.
Okay.
So better will be 111. Easy to growth on 111 plane than 100. Actually, it's like orientation. How we are like taking out the ingot from that liquid.
Yeah. So it will
So
depend on the initial seed, right?
yes, ma'am. Yes, right.
So we can give any seed, no? Like 100 seed, 111 seed, or it's not like that.
Mm,
Kamal?
yes, ma'am.
Yeah, we can give any seed. Like why? You said uh, you said some orientation is
Actually,
better, right?
yes, ma'am. Yes, ma'am. That 111 orientation is like best, but 110 some difficult, then 110 more difficult.
Okay, that might be true, but I'm not remembering what was the reason for that.
Okay, okay, ma'am.
Yeah, but definitely, yeah, Silicon 100, it's not popular because of the growth method, I think. Okay. Lower interface trap density after oxidation. Lower fixed oxide charge after oxidation. So these both are regarding the native oxide growth. So SiO2, when we are growing on top of silicon, uh, it's actually true that lower there will be the defects of fixed oxide and interface trap density will be lower in case of 100 than compared to 111. So it's something like 100 will have some so when oxygen is interacting with silicon, right? So it will see some silicon based on the orientation of silicon, it will see the number of silicon at the surface, and based on that number it will actually be true that the interface trap density that is formed after oxidation is lower for 100 and even the fixed oxide charge is lower for 100 compared to 111. And these two are the reasons that primarily 100 is preferred over faster rate of native oxide growth. Again, that's not the case. In native oxide growth, we care more about the quality of the oxide than the rate of oxidation. Like if you just want a faster oxide growth, we can use some other techniques for growing the oxide on top of silicon. But we are going to native oxide so that we get a good quality, like good quality SiO2 on top of silicon. Okay, halogenic oxidation at temperatures above 1100 degrees Celsius is useful for. So halogenic oxidation basically means that we are oxidizing it in the presence of some halogen like chlorine gas or something. So what do you think that will help in reducing? So chlorine will actually form salts with things like sodium ions or potassium ions, so KCl and ACl salts. So that is why it will help in reducing the mobile charges in SiO2. So that is its primary aim. So we do halogenic oxidation just for this, and so there is one more answer again here that is true. So uh, it also helps in trapping silicon interstitials, and because of that there will be a reduction in the stacking faults in silicon. So these two are the correct answers. I don't know what more to explain on this, but yeah. So, what are these stacking faults? I can maybe talk about that. So, these stacking faults are basically when I am doing a native oxide growth, my getting oxygen is coming inside the silicon, right? So, it's diffusing inside the silicon and forming SiO2. But at the same time, once some amount of SiO2 is made, the silicon will is also in bulk in the substrate and lesser in the SiO2 region. So, it will also start to diffuse in the SiO2, and that will result in formation of silicon interstitials, and that causes this stacking fault. So when I now remove this SiO2, uh, I will see some kind of ridges on the silicon surface. So silicon surface won't be smooth anymore even when the SiO2 is removed. So that are the stacking faults, and that can be reduced because of this halogenic oxidation. So people have noticed that when they do a halogenic oxidation, um, this interstitial silicon will somehow get removed. Like I don't know the exact mechanism. So these two are the correct options here. Okay. In diffusion, what limits the highest doping we can achieve? Solid solubility of dopant in silicon. Okay, that is definitely true, right? Solid solubility will definitely limit the highest doping that we can have. So it basically tells us how much of my diffusing solid is the maximum amount of. So by definition, it limits the highest doping that we can achieve. Maximum amount of the solid that can be dissolved in the bulk. Dopant activation. So yeah. So when we are talking about doping, we just don't want the diffusion of the solid into the bulk, right? We also want it to be electrically active. So some dopants are in general say if I'm doping boron and silicon, the amount of boron that gets diffused in silicon will will usually be same as the amount of active boron in silicon. So electrically active boron. However, if I am doing arsenic diffusion, arsenic might not sit at say the right sites, or it might not to uh, contribute to the dopant energy levels very well in silicon. So based on the choice of dopant and the bulk, it will decide which dopants are active. So it might happen that you have diffused a lot of material, but not all of it is active. So that is the second limiting factor. So these two are the correct options here. Third option is amount of dopant that sits in substitutional sites. Uh, for some reason, they have not said that this is the correct option, probably because um, we can do some post processing to make sure that it sits in the substitutional sites once it is deposited, like say anneal it, or yeah. Like dopant activation takes care of all these things. So once the dopant, like how much amount of dopant is active, uh, will tell the amount of doping that we get. Yeah, damage caused by the silicon lattice due to introduction of dopant. So yeah, this can also be managed by annealing. So whatever is the damage caused, we can just heat it to a higher temperature and then make sure that all the silicon sits back in the lattice positions. Okay. Which of the following are the reasons why gallium is not typically used as a p-type dopant? So again, the image is self-explanatory here. Can you tell the answers? So in the image, we are showing the diffusion coefficient in SiO2. So the gallium diffusion coefficient in SiO2 is way higher, 10 power minus 11, compared to all the others, which are in the range of 10 power minus 16, 17, like that. So it means that gallium will diffuse very fast in SiO2. And for diffusion, we usually need a hard mask. We cannot use a photoresist or something. We need a hard mask. We need an SiO2 mask, and then we will we'll diffuse the different materials, and we should make sure that there is a high contrast between the diffusion through SiO2, that is our hard mask, and the silicon. So it should diffuse through silicon, but it should not diffuse through SiO2. And we see that it is gallium is clearly diffusing uh, very rapidly through SiO2, and that is the reason why we cannot use it as a p-type dopant in silicon. So cannot be masked by SiO2 and very high diffusion coefficient. Which one of the following statements are true about PECVD, plasma enhanced chemical vapor deposition? It can give the best quality silicon dioxide. It can be operated at relatively low temperatures compared to other CVD techniques. It can give higher density of films. It can give higher diffractive index of the films. Which one do you think is the right option? So, okay. In chemical vapor deposition, we'll send chemical vapors and they react and uh, form our thin film on the substrate. Now, for this reaction to take place, we can either to enhance this reaction, we can go to higher temperatures, or what we can do is we will use something like plasma enhanced. So, the plasma will basically uh, do some action like sputtering or like hit the surface, and that will make the surface more reactive. So it will initiate the reaction in a way. So when we are doing plasma enhanced CVD, the entire purpose is that we should be able to go towards lower temperatures. So we don't want to go to higher temperatures. That's why we are doing plasma enhancing. So it can be operated at relatively low temperatures compared to other CVD techniques. So this is definitely the correct option. It can give best quality silicon dioxide. Okay, so if you remember one of Sushoban sir's class, yeah, you're right. Second option is the correct option. Do you think first option is correct? Hello. Correct. Huh? First option. So if you remember the lectures, sir had told that whenever we are doing deposition at higher temperature, that is always the best deposition. So whenever in any process that we are doing at a comparatively lower temperature, just like in case of PCVD, we do it at lower temperatures, the quality will be compromised. So even though we can get relatively good deposition rate even at lower temperature, the quality will be compromised, and that's why it's not the best quality SiO2. So one is false, second one is true. Turns out that the third and fourth are also true. Um, I'm not sure of the reason, but yeah. So you can remember for the timing that it also gives higher density of films, and so since we can get higher densities, it means that we can also get higher refractive index. Uh, Reason I don't remember. I just remember that in class sir had showed some table, right, in which he had compared the quality of film for different. He had compared quality of films for different processes, and he has shown that higher temperature processes are usually giving better quality of films. And in the same table, he had also discussed the densities and refractive indices. And PCVD actually gives very good density of films. So the reason, like physical reason behind it, I don't remember, but it gives very good density and very good refractive index. So yeah, so second, third, and fourth are the correct options here. Okay, so the last question: which one of the following statements are true? Copper is one of the most deadly metal impurity that can diffuse rapidly in your device. In zone defining, purer solid is obtained when distribution coefficient is larger. I have a copper antagonist. If the goal is to prevent contamination, my anneal times can be higher at 500 Celsius than at 300. In the process of creating etheric sites. Okay, we'll go one option at a time. First option, is it true? Uh, can copper, like metal impurity, diffuse very rapidly in our devices? True, right? Like any metal impurity is quite deadly. Metals diffuse quite fast in silicon, and so yeah, one is definitely true. Second option, in zone refining, purer solid is obtained when distribution coefficient is larger. So what was distribution coefficient? Distribution coefficient is basically, uh, yeah, so like, so we have a solid, uh, so what we are doing is zone refining. We have a solid, we are melting it. So the impurity, whether it likes to sit in the solid or in the melt, That is decided by this distribution coefficient. So it basically tells us the concentration of the impurity in the solid upon the concentration of impurity in the melt. So is it better for the impurity to sit in the solid or in the melt? Of course in the melt, right? Uh, so if we want to remove the impurity, we want the crystallized solid to be as pure as possible. So we want the distribution coefficient to be very small. So like the concentration in solid should be very small compared to the concentration in the liquid. Concentration of impurity in the liquid. So the period standard obtained when distribution coefficient is larger. This is false. Distribution coefficient has to be as small as possible. So this is false. Third option, I have wafer with copper interconnects. If the goal is to prevent contamination, my anneal times can be higher at 500 degrees Celsius than at 300 degrees Celsius. Okay. So if I'm making copper interconnects and I've already told that copper can diffuse very fast in my device. So at higher temperatures, if I'm giving higher time, so it will give it more time to diffuse into my active layer. So my interconnect metal can go diffuse into the active device layer, and that can cause problem in my device. So ideally at higher temperatures we should give lesser time compared to the lower temperatures. So this is opposite, so this is false. In the process of creating gathering sites in silicon wafer, it is not possible to reduce the oxygen concentration below 1 ppm in the denuded zone. So yeah, what was gathering? Gathering is, yeah. So if you remember, Chakralski silicon usually has a lot of oxygen present in the wafer. So the distribution coefficient is quite low for everything else compared to oxygen. So because of that, it's very difficult to remove oxygen by float zone or Chakralski methods. And so there will be some oxygen present in the wafer. So usually what they'll do is they'll try to out diffuse this oxygen. So that can be done. Uh, yeah. So gettering is a process of removing impurities in which like okay, so I have a silicon, top layer is my active layer and the bulk is not active. So the in the bulk if I'm able to remove the impurities from the active layer and diffuse them into the bulk, I'm good to go, right? My active device layer will still be able to function well. So one way to do this is by using gettering. So there will be some oxygen interstitials in the silicon bulk, and uh, they will create clusters of SiO2 at some selected positions in the bulk of silicon, and they make sure that all the impurities get diffused to these clusters. So this process is called gettering, and I don't have any pen here. That is the okay. So in short, what they will do is they will first of all put the wafer in nitrogen ambient. So whatever oxygen is present close to the active layer, it will diffuse out of the silicon. So now the oxygen is present only in the it is not there in the active region. It's present in the bulk but not in the active region. So not near the surface. So now this oxygen that is present in the bulk, they will nucleate it by certain processes, and some nuclei of oxygen that form, that they will become the gathering sites, and the impurities from the active layer or like oxygen impurities or some other impurities also, they will diffuse to the gathering sites. So question is, it is not possible to reduce the oxygen concentration below 1 ppm in the denuded zone. So denuded zone is the active region, or the place the region close to the active region from where we have removed the oxygen by out diffusion. So is it not possible to get concentration below 1 ppm? That's not true. Actually, the entire gathering process depends on the fact that we are able to reduce the concentration of oxygen in the active layer to as low as possible. So this is also false. So only the first statement is true, rest of them are false. Okay, that's it I had for today. Yeah, I I'm not really in like in my hostel or so I didn't prepare much. I'm in my hometown. So if you have any questions, I'll share it with you. So this is the last class. If you have any questions, I'll just mail the solutions, or we can discuss like in person if you want to meet.
Okay.
Yeah.
Ma'am,
Yes. Come on. Yeah.
ma'am, please, yeah, ma'am, can you please open the like assignment part in the NPTEL?
NPTEL
I just
assignment.
want to ask this. Yes, yes.
Okay.
Ma'am,
This
like
one.
please open the week one.
Week one.
Yeah,
Okay.
like week one. Yeah. Ma'am, see at the last, it's written like week one assignment solution.
Just a minute. I have to sign in again, I think.
Yes. Okay.
Week one. Solutions. Okay.
Yeah. Week one. Yeah. Like week one is having the assignment solutions.
Okay.
Just whatever it is.
Huh.
Yeah. So, ma'am, my question is like that. Suppose if you will go to week four.
Okay.
Yeah. So, ma'am, just when you open it, like it's not having the solution week four assignment solution like that.
But they have given the answers, right? It's the same thing in the solutions also.
Yes.
Yeah.
Yes, ma'am. Yeah. So, my question is like, ma'am, suppose you are seeing the fourth question. Fourth question.
Yes.
In that, actually, no formula is written over there. Maybe suppose if anyone don't know which formula can we use for solving this question, so how he will know that thing? Actually, my question is like that. So, is there any like PDF that having the solution of all these question, like how this solved by using this formula like that?
Uh, I don't
Maybe
know.
it's like general question. Yes,
So the
ma'am.
TA who is managing these
That
questions, right, and the solutions, that person is not me.
yes, ma'am.
So I'm only responsible for taking these
Okay,
online
okay.
classes. Yeah, there is one more person who is
Okay,
checking all
so
your assignments. You can mail to them. Yeah.
okay, so ma'am, can you have mail ID like if you know?
The other person's mail ID. Or what you can do is you can put
Yes.
in this. Where was that? Ask a question, right?
Okay, okay. Okay, ma'am. Okay, and if possible, if you have any contact with them, can you share this question with them?
Right. Getting formal solutions, right, of all the questions. Like, okay.
Yes, ma'am. Yes, ma'am. Right.
Yeah. Okay. Yeah, I don't know yet. I can ask
Okay,
professor.
okay.
Like
So you
I am in contact with Shankar sir and even Sushoban sir. I can ask them. I don't know who is managing the like who is the TA. I don't know.
okay, okay. No issue, ma'am. No. But
No.
you understand now, ma'am, my question?
Yeah, I understood. Like you want solutions to this, like some written
Yes, yes,
solutions.
yes.
I doubt like this course is running for a very long time now, and I think they are just showing such feedbacks. Like I even have
Okay.
last
Means
year's.
like
Uh,
means I don't want like every each and every question solution. Like just whatever question is having some like problems like situation only for that thing.
You
So it will
can
be
do one
easy.
thing. If
Mm.
it's not much, a few questions I can solve it for you and give you.
Okay, ma'am. Okay, okay.
Just
Okay, ma'am.
write to me.
If
I'll solve the questions, or at least find the formula if it's easily found and give you. If I don't know, I'll ask prof if they have some solution manual like thing.
okay, ma'am. Okay. Okay, so I will prepare one like I will write the question and I will scan it and I will send you via mail. Okay, ma'am.
Okay, yeah, that will. Yeah.
Yeah.
Okay.
Yeah. Thank you so much, ma'am.
Yes. Thank you. So yeah, I'll stop screen share. We'll close today's session. If you have any doubts, you all know my email, right? Yeah, thank you, Sarla.
Yes, ma'am.
Yeah, okay. Thanks. Bye bye.